Hello all and welcome to this video as we continue to look at circular functions. Today we're going to look at graphing sine and cos graphs with, as we can see here, we've got a transformation in here which happens to be a horizontal translation, and we'll also actually be looking at exercise 6G where we'll be adding a plus or minus k. And I haven't changed these, but we've been using the terminology b plus or minus h. And that's a b there, and that's plus or minus h there. So I forgot to update those slides just there on the title. But that's what we're dealing with. B we use when we're trying to find a period, as we've got here. A out the front is our amplitude, h is our horizontal translation, and then when we get to it, k will be our vertical translation. Just like pretty much all the other functions we've looked at so far. Just a quick reminder. To read our b and our h values properly, we must factorize out the b. So for whatever this g of x is inside sine, whatever this function may be, or expression, we need to factorize out to get t by itself, so that we can properly read the b value and we can properly read the h value. So just a reminder there. Well, that's what we're looking at today, is graphing both of these. I should also say up front, this is going to be a longer video because we're covering so much. Just moving my mic. Yeah, because we're covering so much, but I think they tie really well together because it's the same skills over and over. The biggest part of the work is finding the X-Intercepts, just because of having to solve circular functions and the symmetry and all the values that we can get. I spent a lot of time going over that. I made 2 different videos for exercise 6E, so if you're still struggling with that, go back, watch both of those, go back, practice that. There will be times where I'll go through that quickly today, and I'll even use our CAS to show you how to solve and get the values quickly. This is actually a really great way to practice using your CAS, is do it by hand first, then jump on your CAS, see what answers your CAS give you, CAS calculator, so that you're practicing your CAS skills, but also getting your by hand skills. So that's what we'll also try and put in today. All that said, let's get going. Right, I hope I clicked on the right side. So as obvious, it's a sort of 4-step process that we're going to go through, or 5-step. I'm going to call this actually step 0 up here because we want to put that in. If it's not factorized like it's shown here, we need to factorize so that we can read our b and h values properly. So that's almost effectively step 0, is factorize inside the sine or the cos. From there we get our amplitude, which is our a, get our period using our b, find the endpoints, which is just substituting in our domain. So a lot of the time we'll be given where like x might be between 0 and pi. So we'll literally just sub 0 and pi into the equation to get our 2 endpoints, and then from there we need to find our x and y intercepts where they may or may not be present. At the moment, because unless you've got a really small domain, so you might like the regular sine graph, because at the moment we're not giving any vertical translations, unless our domain is really small, like it might just get rid of everything there. Unless we've just got this little peak here, we're pretty much always guaranteed to have some form of x-intercepts. Once we start throwing in vertical translations, we might actually end up with something like that up there that never touches the x-axis. But we'll get to that. So, first example, which is written in the full slide, so you can go back, look through as much as possible, as much as you want, is this one: y equals -3 cos 2 all by theta plus pi on 2. And it says showing one complete cycle. So this is a little different. This leaves it a little bit open to interpretation. You can choose where to do this graph. It just needs to show one complete cycle. Being a cos graph, we know it's usually... let me do that again. An untranslated one is usually like that. That's one complete cycle, so we could draw it between 0 and, well, 2 pi normally, but this is dilated where its period is only pi. So we know it goes from 0 to pi. But we can also see our h value in this case is -pi on 2. So just like always, change the sign of the h. So this means the whole graph has been shifted -pi on 2 that way. So that gives us this endpoint showing this one complete cycle is, well, instead of going between 0 and pi, which will actually sort of look odd for the cos graph, let's go between, instead of starting at 0, let's shift it all the way to negative pi on 2, because we're going 0 take away pi on 2, which is our translation, which gives me negative pi on 2. And then also my other endpoint, which we'd regularly consider it pi, since that's one period. Let's go pi, take away pi on 2, which just gives us pi on 2. So we would end up sketching between negative pi on 2 and pi on 2 to do one complete cycle. And that's what this here talks about. And then from there is just, because we've chosen that, we could have chosen to go between pi on 2 and 3 pi on 2. That would also show one complete cycle, because that's a distance of pi. We could have gone from 3 pi on 2 to 5 pi on 2. Also shows a complete distance of pi. So you can choose where you want, as long as you're showing one complete cycle of length pi. But we've done that one. So we substitute them in, which is what's happening here. For theta, we've substituted in negative pi on 2, which I've put in red. And then you just do your solving. So cos of 0 gives us 1. So we end up with negative 3. And because it's one complete cycle, well, it's going to, if that point, well, this case, that's positive, but in our case, it's actually negative 3, because it's a negative, it's been reflected. It's down here doing something like that. Because it's one complete cycle, wherever it starts is where it needs to end. So once you found one of the endpoints, if you're doing one complete cycle, you get the second endpoint automatically as well. That's not always the case. Sometimes you'll be given a domain that is a half of a period, or 3/4 of a period, or 2 1/5 of a period, so you can't rely on it being whatever the start point is the same as the end point, but for one complete cycle you can. You could also go on from here to find the X-Intercepts. We'll just leave it for now and get into our graphing skills, but you would just go, okay, well, our X-Intercept, we would let y equals 0, and we have to solve, and there'll be plenty of examples of that in this slides. So this is all our information. We have an amplitude of 3, period of pi, y-intercept of 3, which we could have solved by subbing in, it's not on here, but we got that by subbing in x equals 0, or theta actually. In this case, we let theta equal 0. The horizontal axis is theta. And we got endpoints negative pi on 2, negative 3, and pi on 2, negative 3. So let's put those in. Negative pi on 2, negative 3 is there. And another endpoint is there at pi on 2. So, and we want to label them. And that's negative pi on 2, neg 3. And this is pi on 2, neg 3. And we can think of, like I've shown before, we can split, in this case it's reflected, so I'll draw it reflected. We can split our graph in half, and then we can split into quarters for the length of the graph. So if this is at negative pi on 2 and this is at pi on 2, well, the top point, and we had our y-intercept was 3, which is up there. The x-intercepts, without even calculating them, we know they have to be halfway between 0 and pi on 2, which is the same as pi on 4. So we can put them there. And then now we've got all of that, and we know the shape of a cos graph. There's our graph. Now my lines are a bit squiggly, but we get negative pi on 4, 0, and we get pi on 4, 0. And done. So key things there was do your endpoints first, and that'll help, and then look at the amplitude, so the size, and also if it's reflected or not. And you can do little sketches like I did on the previous slide. I just thought, what does a regular cos graph looks like? Well, it looks like that, but it's reflected, so I'm going to draw it like that, and then I also know it's being moved to the left, so I'm going to have something like that. And you can do a couple little sketches beside your graph just so you have an idea of what it's going to look like, and then you can roll from there. Rightio. So let's find, if we need to find x-intercepts, let's talk about that. If it's not so obvious, or we can think, oh, let's just split our function into quarters. How do we actually go about finding them? Well, you would to find an x-intercept, we let y equals 0. So in our case, we've got some new function here. We would have 0 is equal to 3 sine 2x minus pi on 3. So we've got a circular function, a trigonometric function that we need to solve. Now, when we're solving these, we need a working domain. And in our case, we were given our original domain as 0 to 2 pi. And I'm going to go over this fairly quickly because, again, go back to 6e if this is confusing. That's where all of this is. But we substitute these endpoints into anything inside the brackets, and we get what's called our working domain. So we've put 0 in, there's x, and then solve, and we've also put 2 pi in, and then simplify. I shouldn't say solve, I should say simplify. Both times we've simplified. So our working domain is this, between negative 2 pi on 3 and 10 pi on 3, that we can use as we solve that, which here it is on the next slide. So we've let y equal to 0, which we get there. Divide both sides by 3. Well, 0 divided by 3 is just still 0. And then in here, what we're really getting is 2x minus pi on 3 is equal to the inverse sine of 0. Now, what's this inverse sine of 0 asking? Is pretty much what angle gives a, and since it's sine, a vertical component equal to 0. What angle? Well, an angle of 0 does, an angle of pi does, an angle of 2 pi does, an angle of 3 pi does, an angle of 4 pi does, an angle of negative pi does. All of those give us a vertical component of 0. Now this is where we have to go back and reference our working domain. We're between negative 2 pi on 3 and 10 pi on 3. So we actually get to exclude the 4 pi and the negative pi because they fall outside. Because negative pi would be the same as negative 3 pi on 3, and that's too big that way. And then 4 pi would be the same as 12 pi on 3, which is past 10 pi on 3. So yeah, both of those get cancelled. And then all you do is follow on the process of doing your arithmetic to eventually work to get x by itself. So this should actually say x there. And then we get that. And then if we go back, now that we've solved to get x by itself, we can check if these are inside our original domain, which was 0 and 2 pi, which that does, 11 pi on 6 is less than 2 pi, because 2 pi would be the same as 12 pi on 6. So there's our intercepts. So we found our intercepts. So we'll do a practice at just finding intercepts again, which is, again, it's just more practice from 6e, and that's why I stress so much time on it. So we let y equal 0, and we get 0 is equal to 3x plus y on 4. And I'm going to find my working domain straight away. So that's going to be, I put 0 into there, and I also put pi into there, so I'm going to get 3 by 0 plus pi on 4, and I get 3 by pi plus pi on 4, which simplifies to 3 pi on 4, and pi plus pi on 4 is 5 pi on 4 times by 3 is 15 pi on 4. So there's my working domain that I'm going to use. So we can actually let's make it equal 0 on this side. So now we get cos of 3x plus pi on 4 is still equal to 0. Divide both sides by 4. 0 divided by 4 is 0. So we get 3x pi on 4 is equal to the inverse cos of 0. So again, this is asking what angles, and because it's cos, what angles give me a vertical horizontal component of 0, because cos is asking for horizontal component. Well, that's going to be pi on 2 and also 3 pi on 2 will work. So we get 3x plus pi on 4 is equal to, and let's just pi on 2, 3 pi on 2. If I kept going around, I'd also get 5 pi on 2. And because that's a whole rotation and then another pi on 2, and then I could also go, so that's around to there, which is 5 pi on 2. Then again, that's 7 pi on 2. And let's now check against our domain. So I need 3 pi on 4. Well, pi on 2 is less than that, so we get to scrap that. 3 pi on 2 works. 5 pi on 2 works. 7 pi on 2 is the same as 14 pi on 4, so that works. And then if I kept going around, that's the same as 9 pi on 2, which would be 18 pi on 4, so that doesn't work. So in this case, I'm going to have 3 intercepts, and then I just start solving from there. So I get x plus pi on 4 is equal to 3 pi on 6. I'm just dividing everything by 3. 5 pi on 6, 7 pi on 6. Then I get x is equal to, now I'm going to take away pi on 4 from everything. To get common denominator, I'm going to change everything to pi on 12. So that's going to be 6 pi on 12. And now pi on 4 would be the same as 3 pi on 12. 5 pi on 6 converts into 10 pi on 12. Take away 3 pi on 12. And 7 pi converts into 14 pi on 12. Take away 3 pi 12. And that gets me x is equal to 3 pi on 12, 7 pi on 12, and 11 pi on 12. Now let's check for our original domain now that we've got x by itself. That works. All of those are between 0 and pi, so that is fine. That's our intercepts. Now, how could we check this using our cas? Well, it's just a matter of solve, so we can put the whole equation in. We're trying to solve for cos. Let me use the actual keyboard so you can see everything I'm doing. 3 cos bracket x plus fraction pi divided by 4 close bracket equals 0. That's what we're trying to solve. Now, if we do this, we're going to actually get a weird answer. Pi constant 1 divided by 3 minus 5 pi on 12. What the hell does that mean? Well, we've given it no domain. So this is really what that's actually saying. That constant, we could just call it an n, maybe. So x is equal to pi n divided by 3, take away 5 pi on 12. Where n is any integer. Okay? Any integer. I can make that 1, I can make it 2, I can make it 3. And as I keep substituting those numbers in, I'm going to keep getting these solutions here. I'm going to get my first solution, second solution, third solution, fourth solution, fifth solution. So instead of having to do that substitution, what we can actually do to our solve is actually give it a domain. Just like we can give a function, we can give a solve a domain. So we can go into math 3 and use this straight up and down line. So given, and we want between 0 and x and pi. And now if I execute, I get pi on 4, which is actually the same as 3 pi on 12. So that one is right, 7 pi on 12 is right, and 11 pi on 12. So there's my x-intercepts. And we're at 20 minutes already, and all we've done is just done one graphing example and found some x-intercepts. And we've got a couple of, we're going to use that now, used our intercepts, and we're going to plot this. To be aware, we're now also after this going to go into 6G and look at graphing with horizontal and vertical intercepts. So if you need to have a break or go back and rewatch this, pause it after we do this sketch when we go to do 6G. But I'm going to put them all in one video. Right, so we found our intercepts were 3 pi on 12, 7 pi on 12, and 11 pi on 12. 7 pi on 12 and 11 pi on 12. So we can also read off our amplitude is 4. That was our A value. Period was equal to 2 pi on, that's our B value of 3. Our endpoints I've actually already calculated for you, but you could just substitute in 0 and pi and you would find that it's negative 2 root 2 and 2 root 2. And the y-intercept also being one of the endpoints is negative 2 root 2. Now, we need to estimate roughly what root 2 is. Root 2 is about 1.4, so 2 times that is roughly equal to 2.8 something. So let's put them in. Start with our endpoints. So we got 0, negative 2 root 2, which is about 2.8ish. So there, negative 2 root 2. I also have at pi 2 root 2, which is about there. That's pi 2 root 2. What I would then do is from my starting point, I would just go one period and put another dot at that exact point, because that's what a period means. I'm back to the exact same point, so I'm back to there, and so I know that there's going to be a period in this zone. So halfway between, I'm going to know there's a period in there. Now let's put in our intercepts, and that then will help us connect the dot. So we get 3 pi on 12. Now this is pi on 3 here, so half of that there's pi on 6. That means that's pi on 12. That there would be 3 pi on 12. So our first intercept is there at 3 pi on 12. I also have 3 pi on 12, 7 pi on 12. So 7 pi on 12, pi on 3. That's the same as 4 pi on 6, which is the same as 8 pi on 12. So there'll be an intercept there. And then there's another intercept at 11 pi on 12, which is there. Okay, so these dots are looking a little odd, and that's because our start point and our end points aren't at the maximal domain. The maximal domain is 4. So, the maximal range, sorry. So our line needs to get up to 4, and also needs to get down to 4. And that's why the intercept isn't halfway between that dot there and that dot there, because they aren't the peaks. That is one period occurring between those two zones, but they aren't the peaks. From this, a peak would have to occur between the two x-intercepts, so that would be there. Peak up there. There'll be a peak down here. There'll be another peak there. So now we can finally connect the dot. That is a rather terrible squiggly line down here, but you get the idea. And we'd have to label intercepts. So we had, what was that? That was 3 pi on 12, 0. This was 7 pi on 12, 0. And this was 11 pi on 12, 0. Okay. So this was a bit more complex than the previous graph. And why was it more complex than the previous graph? The previous graph, our two endpoints were also our maximum points at -3. So that made it really easy to interpret, okay, well, halfway between that will be my other maximum point, halfway between the max and I guess the min point, I should call these mins, halfway between the max and the min will be my intercept. With this problem here, you need to realize, okay, yeah, my endpoints are at -2 root 2 and 2 root 2, but my maximum and mins will be 4 and -4. So you just can't go halfway between the first endpoint we found and then a period later. That's not going to be my opposite max. Had to recognize that. So how do I find where the maxes are? Well, the maxes will be halfway between the intercepts. So in this case, I had found the intercepts. Okay, so 3 pi on 12 and 7 pi on 12. Halfway between that will be 5 pi on 12. The max and mins will always be halfway between the intercepts. So I'm noticing here, if we look at the graph, I've got 4 divisions, 1, 2, 3, 4 divisions to go across. So I go 2 divisions there with my max, and then I just work backwards to find this min over here. There's my intercept. I need to go across 2 divisions. I go across 2 divisions. There's my min. Same thing here. Intercept, intercept. My minimum point will be halfway between them, which is there. So that's how I figured out where those were to graph. So a fair bit more involved in that, and really comes down to just knowing the shapes and the symmetries within them. Rightio. Pause now if you need to, but I'm going to keep cracking on with graphing now, not only with horizontal translations, which here we saw this graph looks reflected, but it only looks reflected. Even though it doesn't have a -4, it looks reflected because it's been translated, been moved, so it looks somewhat reflected, but it's not. Sorry, not moved to the left, h in this case. I know h is -pi on 4. Okie dokie. No, that's right. Okay. So same thing, all we're now adding on is our k value. And again, we might be dealing with an easy domain, we might be dealing with a hard domain. In this case, we would notice b is 2, so our period happens to be 2 pi on 2, which is equal to pi. I get to look here, between pi on 3 and 4 pi on 3 is a difference of 3 pi on 3, which is equal to pi. So I'm going to be graphing a whole period in this one, if I was doing this one. So that's a handy thing to note. But again, sometimes we might be graphing, like this previous example, we were graphing 1.5 periods. Same process. Find the amplitude, find the period, find the endpoints, find the x and y intercepts. Again, step 0, I'd say, is factorize as needed. And I've left some of the brackets out. There should be brackets around that. Factorize out the 2 to read the h and the k values properly, or read the h value properly. So here's an example. We have 2 sine 2x plus 2 pi on 3. We need to factorize it. We need to take the 2 out to read the h and k. So in this case, we got h is -pi on 3, k is 1, b is 2, a is 2. So from this, we get period is equal to 2 pi on 2, which is equal to pi, which we can see there. We can sub in the first endpoint, which was -pi on 3, which is doing there, substituting that in. Turns out we get a y of 1. And because our second endpoint is a whole period later, in this case pi, we know it'd have to be the exact same value. So that's a little shortcut in working out, but again, you could substitute in 2 pi on 3 and you'd still get y is equal to 1. From that, we've got amplitude, period, endpoints. We need to find our intercepts. We know there'll be x-intercepts. This is one thing to check now that we've got vertical translations is the amplitude greater than the vertical translation? Because if not, then we might end up with something like this, and you spend a lot of time trying to figure out what your x-intercepts are when they don't even exist. And that might occur in something where it might be y equals 2 sine x plus 4, because the plus 4 moves it up greater than the 2. It'll never touch the x-axis. So let's find our x-intercepts though. For this case, we're going to let y equal 0, so we get 0 is equal to 2 sine 2x plus 2 pi on 3. And I'm going to put the 0 on the other side. And I'm also going to find my working domain straight away, which is going to be 2 by -pi on 3 plus 2 pi on 3 and 2 by 2 pi on 3 plus 2 pi on 3, which works out to be 0, and 2 by 2 pi is 4 pi on 3, 6 pi on 3, which is equal to 0 and 2 pi. Well, that's a nice working domain. From here, we're going to go back to our equation and start solving. So we get sine 2x plus 2 pi on 3 equal to 0. So we get 2x plus 2 pi on 3 is equal to the inverse sine of 0. This is actually pretty. I've forgotten the plus 1. I was thinking that was looking too easy. Plus 1 is equal to 0, so we get is equal to negative half, because I take the 1 over, it's minus 1, then I divide by the 2, so that's better. That's where these become harder. As soon as we start getting vertical translations, we avoid getting a 0 in here, which means it's generally a bit harder. You need to think about where that is. So sine of negative half, that is asking what angles are going to give me a vertical component of negative half, which would be sort of the same as here, negative half. That's where they occur, and that's between 0 and 2 pi of our working domain. So what angles? Well, the reference angle to get in there is pi on 6. So the actual angles are 7 pi on 6, and all the way around is 11 pi on 6. So that's my 2, and then I just do the arithmetic from there on out. I'm going to go back to blue because that green's probably not the best. So we get 2x is equal to 7 pi on 6, and we're taking away minus 2 pi on 3 from both sides. I'm going to convert it to pi on 6 straight away. 4 pi on 6, and we get 11 pi on 6. Take away 4 pi on 6. Get 2x is equal to 3 pi. So we get x is equal to 3 pi on 12 and 7 pi on 12, which I could simplify the first one to pi on 4, and the second one doesn't simplify. It leaves us 7 pi on 12. Let's double check that. We can just highlight our previous one, drag and drop, and we had 2, and that was sine 2x plus 2 pi on 3 all plus 1, and we're letting that equal to 0, and we're doing that between negative pi on 3 and 2 pi. Pi on 3, hit incorrect parentheses. Oh, that needs to be that side of the 0. Oh no, that doesn't need to be there at all. There we go. There we go. Pi on 4, 7 pi on 12, so all the work we did was correct. Rightio. So from there, we found already our amplitude is 2, our period is pi, our intercepts we said was, I'm going to actually leave it as pi on 12, what was that? 3 pi on 12 and 7 pi on 12. I just find it when they're written in the same denominator a bit easier to plot. And again, I found the endpoints for you was negative pi on 3, 1 and 2 pi on 3, 1. So let's go ahead and graph these. Now, sometimes you're going to be given a graph like this where the grid isn't very helpful for the type of problem, like especially trying to plot 7 pi on 12. Because in this case, we've got pi on 3 going across, and then we're over at 2 pi on 3, which is, if we want to simplify, this is the same as 2 pi on 6, and this is 4 pi on 6, or this is the same as 4 pi on 12, and this is 8 pi on 12. So if I want to find where pi on 12 is, well, 4 pi on 12 is here. Well, that means I've got to divide it by 4, but I'm given divisions of 3, which is terrible. We would want to actually go, that's about 1, 2, 3. So now I have, there would be pi on 12. So you've got to be really careful with the grid that you're given. Is it something useful? So whatever the value you are given, in this case pi on 3, convert it to the denominator that you are using for your intercepts, and then you can figure out how many times you need to divide it down to be able to put your X-Intercepts in correctly. So that's my hint to you. It is handy for our endpoints, but yeah, for the actual X-Intercepts, not so great. Now we need to, let's put in our endpoints first. That's what we should start with. So endpoints negative pi on 3, 1, and also 2 pi on 3, 1. Put those. My cat's meowing at me. She wants extra food. Next are intercepts. So 3 pi on 12, which will be there. And 7 pi on 12, which will be there. So it's quite obvious to see that the graph must come down. Something like that to actually make it work. So from there we can tell, okay, where do we find our min and max points? Well, our amplitude is 2, but we're plus 1, so our graph is actually oscillating about this line y equals 1. It's oscillating about that, and it goes up 2 and down 2, so our max point must be at 3 and our min point must be at 1. Where do they occur? Well, the min is going to occur between these two intercepts over at the right hand side, so we can put that halfway between them, which happens to be there, which would be 5 pi on 12, negative 1. And then I went across 2 intervals, so my maximum will be going across 2 intervals, so that's going to be up there. And clearly from here, did I put the negative pi on 3? Well, I'm missing an intercept. Am I? 2 by negative 2. Let's plot this out and let's see if I'm missing an intercept. I think I might. Am I? Let's plot it out. We at least get that. That. Oh, no, I put that max at the wrong point. I need to get back to the midpoint. 2 things across from the intercept, I need to get back to the midpoint. There we go, and this is going to be the max. Then another 2. There's 1, 2. So the maximum is going to occur there. There we go. That looks much better scale-wise. No, that's also not working. What have I interpreted wrong here? X-intercept, X-intercept. Max must be halfway between them. Getting to there, right? One more notch across there, so that gets us symmetrical. Okay, so again, we've fallen short trying to interpret. Well, I fell short trying to interpret too much because I didn't go and find what my y-intercept is. I should have found what the y-intercept is by letting x equal 0, so we get y is equal to 2 sine 2 pi on 3, because that becomes 0. y is equal to 2 sine of 2 pi on 3. 2 pi on 3 is over here, so it'll be positive. Reference angle of 2. That becomes root 3 on 2, which is going to be root 3. Again, that's not making sense. Okay, let's graph it. This is where, and this is the process that you should be following. If you're running into these errors where this is where it's completely fine to put in your calculator and check, and then see where you're making mistakes. Oh, because I forgot the +1 off the end. +1. +1. Root 3 +1. That makes much more sense. So that is 0, root 3 +1. Better. There's our graph. Even I still make mistakes. There's a lot of work in it. But let's go back and actually put in 2 sine 2x plus 2 pi on 3 plus 1. We've defined that. I should actually probably define it with the domain. Put that in there. Number of parentheses, yes, there. Define, go to graphing. Let's put f of x in, graph. There we go. And let's do box zoom. Yeah. There we go. So that matches. From here we've got one more graphing example, and then we've got applying our knowledge of transformations to identify or apply transformations. So this one, a bit of the work's done for you already. Y equals 2 cos 2, then all in brackets x plus pi on 2. So it's already factorized for us, this one, plus the root 3 on the end. And we've got endpoints of negative pi and pi. So let's find our working domain straight away. So I'm going to substitute those in. So I'm going to get 2 negative pi plus pi on 4. And I'm going to get 2 pi plus pi on 4. Which gives me negative pi plus pi on 4 is negative 3 pi on 4. So that becomes negative 3 pi on 2, simplifies down, and pi plus pi on 4 is 5 pi on 4 times by 10 is 10 pi on 4, simplifies to 5 pi on 2. So that's my working domain. So I've already done let y equals 0. I've already done the endpoints for you over here as well. So let y equals 0, we get this, so we get cos 2x plus pi on 4 equal to, take the root 3 over to the other side, so we get negative root 3, and then I'm dividing by the 2 out the front, so we get 2x plus pi on 4 is equal to the inverse cos of negative root 3 on 2. So what is this asking? Inverse cos, it's pretty much saying what angle is going to give me, and since it's cos, it's going to be horizontal component of negative root 3 on 2. Well, to be negative means it needs to be over here, and to be a component of, to get me root 3 on 2 is, that angle in there would be pi on 6, and same in there, pi on 6. So the actual angles, or the most basic ones in quadrant 2 and 3, we get 2x4 is equal to, that would be 5 pi on 6 and also 7 pi on 6. But we need to look at our working domain. We've actually got a really large working domain between negative 3 pi on 2 and 5 pi on 2. Negative 3 pi on 2 is going all the way around that way, and then 5 pi on 2 is going all the way around to there as well. Okay? So that includes our pi on 6, our 5 pi on 6 going round, gets it. Keep going around, gets it at 7 pi on 6 going, gets to 5 pi on 2 and stops there. So we don't get them again going around positive way, but we are going to pick them going around the negative. So that's also, move these over a little bit, 5 pi on 6, 7 pi on 6. Coming around this way also happens to be negative 5 pi on 6, and going that bit further also happens to be negative 7 pi on 6. It's pretty rare for that to happen, but it does, where it's the same numbers, just positive and negative. But you got to check it. It's not always the case. And then we just solve from there, so we get x plus pi on 4 is equal to 7 pi on 12, negative 5 pi on 12, 5 pi on 12. Add the pi, we're going to subtract pi on 4 from each of them, which is the same as subtracting 3 pi on 12. So we get negative 7 pi on 12, take away 3 pi on 12. And some of these steps you'll be able to do in your head. I just want to show all the working out. And 12, take away 3 pi. 12, we get negative 9 pi on 12, negative 7, take 3 is 10. Negative 10 pi on 12, negative 8 pi on 12, 2 pi on 12, and 7, 3, 4 pi on 12. All of these can be simplified to pi on 6, so we get negative 5 pi on 6, negative 4 pi, 6, pi on 6, and 2 pi 6. There we go. So there's our intercepts. So from there we can now graph. So what do we get? Negative 5, negative 4, negative 5 pi 6, negative 6, pi on 6, and 2 pi on 6. Yeah. 2 pi on 6. Okay, so let's go and plot everything that we've got. Also noting again, we've got a period of 2, but in this case we've got a vertical translation of root 3. So root 3 is 1.7 something, if I remember correctly. Let's double check. Root 3. Yeah, 1.73. So our graph is oscillating about that sort of line there, doing something like that. So it's a good idea to have that in your mind. Right, first endpoint, negative pi root 3. Okay, so right there. Other endpoint, pi root 3. Put that in. Put in our intercepts. We'll use another different color. Negative 5 pi on 6. So again, I've left, they're all pi on 6s. I could have simplified the negative 4 and also the 2 pi on 6, but I leave them all as the same. It's going to make life a little easier. So I'm going to convert pi on 2 into pi on 6. So that's the same as negative 3 pi on 6. So now I can see what, how much I need to divide between 0 and that point into to get the intervals I want. And I need to, no, that's 1, 2, 5. So that's, again, not a handy division amount. So we need to actually eyeball it. So about there, about there. So that would be pi on 6, and that would be pi on 6, which I actually need. I need those ones. There and there. And then I need negative 4 pi, so I need to split up over here, out there and there. And that's also the ones I need. That's negative 6 pi on 6. So that's my intercepts. I need a y-intercept, so let's find that quickly. So I get y is equal to 2 cos 2 pi on 4 plus root 3. So I get y is equal to 2 cos 2 plus root 3. since there's no brackets there, it's assumed that that's what the cos is applying to. So we get cos of pi on 2. Pi on 2 is there. Oh, it's 0, so we just get root 3. So intercept is there. Okay, rightio. Okie dokie. Right, let's get some patterns going on. Clearly, my minimum at root 3 take away 2. I'm going to have a max also at 2. So my maxes are going to be up there somewhere at this point here is 2 plus root 3. My amplitude plus my vertical translation, and my minimums are going to occur somewhere down about here. That line, which is 2 take away root. No, other way. Root 3 take away 2. Yeah. Vertical translation take away the amplitude. And they're going to clearly occur halfway between those intercepts, so they're going to be there and there. So graph comes down like that. Going to come up, have a max, come down, through, keep this pattern going. There, and there we go. There's my graph. Label my endpoints. That was pi root 3. That was negative pi 3. Intercept was 0 root 3. And I'm a bit tight for space here, but you would label coordinate form your intercepts as well. And when I don't have labels, mark here, which is 5 pi on 6. That's negative 4 pi. Negative 4 pi, this one here is 5 pi on 6. This one's pi on 6 and 2 pi on 6. That's it. That's graphing. So it's a bit of playing connect the dots and also some intuition about the shape of the graph. If you wanted to know where, let me get a different color, this maximum is, well, we know the minimum down here is between negative 5 pi on 6 and negative 4 pi on 6. So halfway between that would be, well, that's negative 10 pi on 12, and that's negative 8 pi on 12. So that there is at negative 9 pi on 12. If that's where the min is, the max distance from min to max or from max to min will be half the period, and then again half the period. So we knew our period was pi, so if this min was occurring at negative pi on 12, half a period would be 6 pi on 12, so this one would have to occur at negative 3 pi on 12. And then a whole pi later, I get another one, because it's another period later and my max occurs. So that's how you could also find those using some intuition about sine and cos graphs. Well, we're almost up to an hour. I really apologize, but this takes ages. When you're first doing it and talking through and showing all the working out, there's a lot to it. Right, finally, using transformations. Okay, find the equation of the image y equals sine x for each of the following transformations. So dilate by a factor of half from the x-axis followed by a translation of pi on 2 units in the negative direction of the x-axis. Well, there's the dash method, and I'll leave that there for you if you want to use it, but let's look using inspection for those replacements. So if we're dilating from the x-axis, we would replace y with y divided by whatever the dilation is. Let's call it a in this case. Okay, so we're going to replace y with y on a, and then we're also going, which is our dilation, that's our dilation there. And then we're going to, by translation of pi on 2 units in the negative direction. So that's effectively saying h is equal to negative pi on 2. So we would replace x with x. We normally do replace x with x minus h. So what are the actual replacements we're going to do? We're going to do y with y on half. And then we're also going to replace x with x. Now, because h is already negative pi on 2 and it's always minus h, so we're going to end up with plus pi on 2. So we put that into our equation. We now get y on half is equal to sine of x plus pi on 2. Multiply the half across to the other side, we get y is equal to half sine x plus pi on 2. My biggest concern and looking at some resits and everything is people are still applying these to the wrong axes or putting the wrong signs in. So you need to go all the way back to that transformation video where we talk about what all the replacements are. Have them written down next to you and practice using them. Work towards memorizing them. So let's do this again as our last example, and then all these exam questions can be for in class. So find the equation of y equals sine x for each of the following transformations. Dilation of factor half from the y-axis by translation of positive pi on 6 units. So here we're going to do replace y. No, we're dilating from the y-axis, so that means we're replacing x with x on b, or whatever our dilation factor is. So that's going to be replace x with x on half. And then we're also going to, that's a really common mistake. People just do x times by b, they don't do x divided by b. And the other one is we're going to replace x with x minus h, and in our case h happens to be pi on 6, so we're going to do x with x minus pi on 6. So we have to apply these in order. We have to be really careful that we apply these correctly in order. So we apply the first one, we're going to get y equals sine x on half, and I'm going to simplify this now before I apply the next one. So we get y equals sine, now x divided by half is the same as x times by 2 on 1, so it's just equal to 2x. And now I'm going to apply the x minus pi on 6, so y is equal to sine 2, and I'm replacing the x, so imagine the x is in brackets. Yeah, because we're replacing directly the x, so it actually turns into 2x minus pi on 6. In brackets, people were not putting that in brackets and they were doing that, which is different. That's wrong. Get that, which is equal to sine 2x minus pi on 3. And that's it. So that's just using our skills of remembering those replacements. How can we apply transformations? I'm going to leave it there. That is a massive video, but it needed to be, combining those two exercises. A lot of the work is all of this. A lot of the work is there, and a lot of the work is there. That's why I stressed 6E so much, because that is all just 6E. It's all just solving trig equations. If you have any questions, please ask in class. Please use class time effectively. Really, really need to. Or send me an email, something on Google Classroom, or put something in the comments below. Thanks, and have a good rest of your weekend.